Thank you very much. Paweł is a pretty difficult name. I'm from Poland. In Espanol, está Pablo. No está fácil. Yes, I work in IoT business for about 8 years so far. And today I would like to tell you a few words about where this business is going, into which direction, because I think the direction is getting clearer and clearer. And when I was starting like 7 or 8 years ago, it was a buzzword. Everyone wanted to do IoT, wanted to sell IoT to customers, etc. But now, so far, people are forgetting about it. But the market is still growing. It's constantly growing, which I will show in the next slide. So, the world has gone edge. What is the future of IoT? Let's start. For a good beginning, the consumption of 0.012 kilowatt hours. Is it much? Or is it not really much? What can we do with such amount of energy? For example, to generate one image in the cloud using generative AI, if you would like to have like a fancy matrix-like looking cats on your presentation, you just put a prompt on a generative large language model and you get a picture, right? It takes like this amount of energy in average, depending on which model you use. But to compare, you can fully charge your iPhone using the same amount of energy. So just get an image, charge the phone. Is it much? It's not too much. Good question. But to have a third comparison, how about having a quite powerful edge device equipped with GPU, which can work for over 1 hour using the same amount of energy, and doing like machine learning for you, AI stuff for you, computer vision, whatever, you name it. I will leave you with this slide for a moment. We'll come back it at the end of the presentation. But now let's start from the very, very beginning about IoT itself. IoT as we knew it, because now as we know it, it's a bit different, but as we knew it a few years ago. According to the definition from Gartner, it is Internet of Things. It's like network of physical devices, physical objects, which can communicate, sense, or interact with themselves, with their internal states, or with the external environment. So more or less everything which has a microphone or camera or another kind of sensor, accelerometer or whatever, and is connected to any kind of a network becomes an IoT, Internet of Things, Internet de las Cosas in Espanol. Market predictions. I had this slide. I love those slides because a few years ago, I was showing those kind of slides to my customers, showing how big this market will be in a few years. So, my dear customer, you have to jump into that train, because now is the time. Now is the time for you to invest in IoT, to get your return of investment, because there will be billions of devices connected all over the world. And check out the date. It's just 2 years ago, even 1.5, when the Forbes said there will be 207 billion devices connected. We have like 7 to 8 billion people living on Earth, right? So it's about 25 devices per person, quite a lot. This made me curious. That was the prediction for 2024. So let's make some calculations. How many IoT devices we have in this room? Let's start from a smartwatch. Who of you have a smartwatch like I have? You have. About 50%. Good. Smartwatch. Is it an IoT? There are several sensors. There is accelerometer. There is a pulsometer. There is, altitude meter or whatever. And it is connected to your phone via Bluetooth. Yes, it's some kind of an IoT device. How about wireless earplugs? How many of you? Even more than 50%. Okay, so now we have like 1.5, maybe 2 IoT devices per person in this room. Still far away from 25, right? The third one, the smartphone. Before you say something, I know all of you have a smartphone, maybe some of you have even 2, but this is not really being classified as an IoT. It is too general purpose. It's like a computer in your pocket, right? So it's not IoT anymore. It's a very powerful device, so we don't have it in those statistics. So 2.5, maybe 2 devices per person. 7 to 8 billion people living on Earth. It's far away from 207 billions, right? So let's have a look, how did it finish? Because that was the prediction for 2024. Actually, in 2024, we had 18.8 billion devices connected, which is true. And we see the market is growing. So we will have like 14% growth every year because we are still designing IoT. We are still building new kind of devices. We are selling them to our customers. So the market is growing, but it's not like, hundreds of billions at the moment, or even maybe in this century, yes, but not now. Till 2030, we should have about 40 billion devices connected. So we know the predictions, we know the forecasts, we know the reality. Let's start from the beginning. How does this thing work? How IoT really functions? Classic architecture. You are the software guys. I believe you love architecture diagrams, right? So this one is quite simple, have just 3 layers. First of all, we have a sensing layer. By the sensor, we mean everything which can, take something from the environment. Microphone, like a camera, like pressure sensor, temperature sensor, altitude sensor, light sensor, whatever. Once I had a project with an American customer who wanted to have 70 different gas sensors to control what is in the air, what kind of gases are in the air, to have like some comparison of the different sensors and different gas analytics inside the cloud environment. So we had like 70 different gas sensors just in one project. There are hundreds of sensors. There are thousands of sensors, maybe even on Earth, which you can use in your IoT projects. And when you sense something, then you need the connectivity layer. It could be a Wi-Fi, could be Bluetooth, could be LoRa, all kind of GSM networks like 4G, 3G, 5G, in coming years also 6G, and whoever know what else. So, and there are also dedicated networks, typically for IoT, like NB-IoT, narrowband or something. When you send your data, you send something, you send it somewhere, you receive it somewhere, so you need to have an application layer. Because that you sense, pressure doesn't bring any value. To have a business value, you need application layer, right? And usually, this is on your smartphone, on your computer, and hosted centrally somewhere in the cloud. So that's the basic architecture of IoT. The process is quite straightforward. You have a device which collects data from the environment, from other machines, whatever. Then you need kind of a gateway which sends this data somewhere from multiple devices. Like at your home or office, you have a Wi-Fi router. A Wi-Fi router is actually gateway. This is the only device connected to the network, which is internet, and all of the other devices are using the router as a gateway to external world. And then the data is sent to a central system in the cloud or your own server. In more sophisticated scenarios, we also have a device taking a simple action by itself. So maybe some examples to make it a bit more interesting now. Smart water metering system. We have to measure like a consumption of utilities, water, energy, gas, wherever we are, in the office buildings, in apartments. And a few years ago, the process looks very simple. Like the guy needed to come to your apartment, you needed to open the door and to show him the meter, right? All over the world. And he just wrote down the number, okay, the consumption is this level. Then he go back to the office and write it down on another piece of paper, or finally place it somewhere in the system. Now, in this era we have now of the IoT systems, the measurement is done automatically. You have a sensor embedded in your meter running on a battery, which is asleep for most of the lifetime. But once a month or once a year, it wakes up, checks the measurement, sends it to the gateway located somewhere in your building or somewhere outside of your building, and inform the company how much they should charge you. Water leak. Let's say you have an apartment or a house and you have water leak detector, which means there is a very simple device having like two cables outside of the box. And those two cables are not touching each other. When this device is lying on the floor and there will be a water dropping on that, those cables will be connected by the water and the electricity started to flow. It's very simple. When those connection between those two cables triggers the alarm, triggers the sensor, then there is some information being sent to the gateway, and gateway actually forwards it into two locations. The first one is to close the valve, to stop leaking. When you are not home, it will save your apartment, right? And the second endpoint is, of course, to inform the customer, which is you, to come back to your home and check out what is happening because you have water on the floor. In this case, we have the scenario when the device is taking a simple action by itself, by informing another device of a situation and closing the valve. So how about something more fancy? Something which is not really written down on the blocks, let's say. Imagine a warehouse. During my career, I received really a lot of phone calls from potential customers asking me to help with their business with the devices, with the smart devices. And one of them, I remember it was Friday morning, I was drinking my coffee, and the telephone rang. I answered, and I heard, "Hi, I am working with the warehousing business, and I need some devices to help me." And warehousing, okay, then I just open my imagination. In warehouse, it is pretty much to do in case of automation, IoT, sensing, whatever. You can have autonomous vehicles. You can have indoor navigation, which is a case still not solved, actually, for most of the warehouses to find the goods, where are they located. You can have RFIDs, locating, etc., sensing maybe if the temperature of the box is proper or not. And I started to talk like that. Then the guy said, no, hold your horses. It's not about robots. It's definitely not about AI, and it's not about any autonomous vehicles. It is about something completely different. It's about a mouse. That was the case. I never supposed to be doing such projects when I started this business, because my customer is actually not an owner of the warehouse. He is providing a service to warehouse owners. And if you have a big warehouse somewhere outside of the city, something which you can see from the highways, it is near the forest, near the fields, actually somewhere outside of the city where a lot of mouse, rats, other rodents, they just live there. And they are really happy to get inside your warehouse and do a little mess inside. So my customer is providing the service, making the protection for the warehouse owners to not let rats get in. So he's actually building the small boxes, which you saw perhaps many times, like the black boxes located somewhere outside of the buildings. Also here, I guess. Yeah? Those boxes contains poison, or there are traps for a mouse, for a rats, for other kind of animals. We received two kinds of the traps from a customer. The one on the top is a mechanical one. It's quite brutal, to be honest, because when the mouse enters, it just breaks the neck of the mouse. But to sense does something happen inside is quite easy, because we have like a mechanical position of the device which changes. So we have one sensor called a contactron. When the positions change, we can send the information to the system that something happened in that. The second one, the steel box on the bottom, is the live trap, which means the mouse can enter but cannot leave. And it stays inside for how long someone needs to get actually to that box and not find that mouse or the rat. So my customer said he's paying really a lot of money to service them, to maintenance those boxes, because they have like tens of them maybe in a warehouse. But if he has like 10 warehouses, there are hundreds of boxes. If there are warehouses located all over the country, you have thousands of them. So someone needed to go there just once a day or twice a day, maybe sometimes, to check what is happening. A huge cost. So he told me, okay, implement IoT device, place them inside that box, and make sure I know that I go to the proper trap instead of going everywhere, right? We used a LoRa communication technology, which is very low power technology, so we can wake this device up only when it's needed, once a day, for example, to send the information. We used some kind of a sensor which is passive. I believe you know that from the toilet use case. And a public toilet, I think all of us had the situation that you sit down on the toilet and you wait for like 30 seconds and the light goes off, right? This is because the sensor is passive. If you don't wave your hand, the sensor actually turns off the light. That's the same situation here. So it does not drain the battery. You could run this device for many years, actually, checking out if something entered the trap, and send the information using your gateway for over 100 mousetraps using one gateway and the LoRaWAN technology to the cloud. And the most important, no animals were harmed during this project. Even my customers asked me multiple times to purchase the mouse to my lab. But I said, no, dear customer, this time testing is only on your side. All right, so 3 examples, 17 slides, and no AI. Oh, come on, this is a software conference. There must be AI on the slides, right? The main topic is AI. So let's change it a bit. When IoT system really needs AI? Because the cases I mentioned, they not require AI at all. There's just pure sensing, connectivity, maybe stopping of some other devices, and that's it. But AI can really help in IoT business as well. Whenever you have too much data to analyze, if in this huge amount of data you are looking for something, you are looking for patterns, anomalies, some predictions maybe, forecasts, and you need to take real-time decisions. So it's like always, like with any kind of a system, but IoT can generate really huge amount of data, which I will show in the beginning. So here comes the architecture with AI processing. We had 3 layers, now we have 4. We add the data processing layer. So let's say the device sends something, temperature or vibrations, through the connectivity layer, sends the information to the cloud, where we have our machine learning called AI algorithm running, being processed, and then the result is delivered to the customer, to the end application, not just the data. How about an example? License plate recognition. We enter by our car, we want to enter the parking lot. There is a camera which is taking picture of the front of the car. These pictures usually not just one, but perhaps few of them to make the proper quality, etc. These pictures are being sent directly to the cloud. And then there are 2 AI models running. The first one detects the license plate on the picture, cuts everything off, everything else, keeps just the license plate. And the second model make an OCR, which is just changing the value from the picture to the real raw text. So we have 2 AI models running in the cloud. You need to send the picture to the cloud endpoint, wait a moment for the response. And then the raw text is going back to you to print the ticket, like the license plate on the ticket, etc. And perhaps some more information if the parking was paid or not, so you can open the gate. The second example is a bit more difficult because it's a predictive maintenance. Predictive maintenance has just one reason: to recognize the failure is coming. You can run it on engines like production lines, maybe pumps, maybe all kinds of industrial devices to make sure you know in advance that you need to replace some kind of parts, for example, or you have to do some other maintenance. And it's very difficult, to be honest, but customers are really able to pay for that because their business stops when the device crashes, right? But if you have an engine like that, which is rotating 3,000 times per minute, which means it is 50 times per second, 50 hertz. The sampling of 50 hertz is not enough to get a proper data for predictive maintenance. You need to sample like 10,000 data samples per second, which is a huge amount of data. And you send it, you stream it directly to the cloud, right? And in the cloud, you have a mechanism, you have a machine learning model who is looking for anomalies, looking for something in this data. So how to make it more efficient? How to not send such amount of data? How to not rely only on the connectivity with your cloud system? And how to save energy? So this is where direction of IoT is actually moving us. Going back to this architecture, we have this data processing layer in the middle. How about we just switch the order and make it like that? So we have directly from a sensing layer, edge processing layer, which is utilizing CPU, GPU, or NPU directly on your device. So we process this data without sending it to cloud for machine learning purposes or for AI learning. If we abandon everything here, let's have this use case with the license plate recognition. You don't have to send the whole picture to the cloud. You don't have to send like 5 pictures or whatever. You don't send anything. You detect the license plate on your device. You cut it off. You OCR it on the device in a real time. It works really fast at the moment, to be honest. And you send to the cloud just the raw text with your license plate, like it was opposite direction before. Just the raw text to make sure this car is allowed to enter or to leave the parking lot because you already paid. And imagine the savings in case of a predictive maintenance, where you don't set this 10,000 samples per second. You keep it on the device. You process them in a real time. So this edge AI hardware It's now actually time of a revolution. It's not even evolution, but it's getting a revolution. We know CPU. CPU is like general purpose. It's in all kinds of the devices, right? It can do everything. Of course, you can run AI or machine learning models on CPU, but it's not like dedicated hardware to that. It will not be efficient. It will consume a lot of power, it will take time, etc. So it's not the best one on this chart, right? FPGA is very sophisticated, but it has nothing to do with the, let's say, AI algorithm at the moment, so just leave it for now. We focus on CPU, GPU, and NPU. GPU, everyone knows that. It's perfect for training. We have GPUs running in the clouds of Amazon, Google, and any kind of a clouds. We have a GPU units running on our own strong laptops to train initial models for the training. And before, a few years ago, we also used GPUs for edge computing. But now, we have a new player, which is called NPU, Neural Processing Unit, which is dedicated hardware, very small, not even generating a lot of heat, a lot of warmth, in comparison to GPU, which is getting really heat very fast. And it can run directly on the device. What we see on this picture, TOPS, is a tera operations per second, which is saying how fast the device is. But the TOPS per watt saves how energy efficient it is. So the CPU will be the lowest, will have the lowest efficiency when we run it on the edge device. The NPU is like 20, 30 times more efficient in this case. So what's actually NPU? If the CPU is a general purpose, like a Swiss Army knife, you can do everything with that. It's not specialized. The GPU is like a jackhammer, it's like a bazooka in military, which is very powerful but brute. Then the NPU is like a precision laser tool, something which is designed to do just one thing. And this one thing is the AI execution, not training. You cannot really train the models running your NPU. You just execute them. So where to use edge AI? Where to use those NPUs, GPUs, whatever? There are three main areas. The first one is embedded vision. Embedded vision is nothing else than computer vision, but embedded on the device, which means we have all kinds of objects detection, recognition, classification, and tracking. For example, counting of the objects, counting of the people, entering, leaving. Face recognition. What else do I have in my phone? But because how my phone unlocks when I just look at it, even if it's in airplane mode, is because of the edge AI model which is running on the NPU, on the phone, right? We have a traffic monitoring. I had one customer in Australia who were actually already utilizing edge AI to count how many trucks, vehicles, and bicycles and motorbikes are running over the intersection, but he wanted to have another class. Uber Eats and Glovo. It's another kind of vehicles for them. So they wanted to track it. We needed to extend the existing models to have another class, also using embedded vision. Pose estimation, so how your hands are moving, how your legs are moving, how the head is moving. I've seen an application for golf players, for example, which are like the online trainer to measure if you keep the golf club in the right position and you do everything well with your body when you're playing, right? And all kinds of seeing by drones, by autonomous vehicles, by robots, etc. Because when you are in your car, which is autonomous, then you don't have time to communicate with the cloud. The decision must be made here on the edge. The second area is about sounding. Detection, recognition of sounds, and speech. I believe many of you already had at home something like a Google Assistant or a Siri or Alexa. And how those things work? They are, of course, connected, and they are, of course, having multiple microphones, listening to everything the people say. But they are not transferring them to the cloud. At least that's what Amazon says. But they're not supposed to. They should wait for a wake-up word, which is, hi Siri, hi Google, Alexa. When they recognize, using the embedded AI model on them, when they recognize the wake-up word, then the stream to the cloud starts. And then you give your command, right? That's why we first have to say Alexa. And you say, Alexa, please play some music. Then it's waiting, waiting, waiting. Sure, here is some music. It's because of the latency and the cloud communication. But the wake-up word has been recognized using Edge. And we have, except of the voice command, we have baby cry recognition, for example, or a breathing monitoring. So you can use your microphone and very tiny little devices running on a battery to recognize if there is someone crying, if there is an alarm siren, or if someone is breathing, one or more people, or the breathing stop, for example, patient monitoring at hospitals. Or machines anomaly detection, because you can use ultrasounds, which are very, very powerful source of data about failures and potential failures in the machines. And the third area is all kinds of the other sensors. So we have a signal processing from vibrations, accelerometers. I already talked about it when monitoring the edge and pumps, etc. Yeah? But we have also all kinds of biosensors, monitoring your heart rate, using the smartwatch, for example, or using the wrist here, the band here. We have fall detection. Because if I have my watch, if I am riding bicycle and I had a hard fall, I hit the car or something and I'm lying down, the watch will recognize there was a hard fall without communication with the cloud. Then, after all, if I don't press the button, he will try to communicate my cell phone and via my cell phone communicate with my family or the emergency service to tell them where I am, right? But the edge is actually working right now, even offline, to say, okay, that was a hard fall. Step scouting and physical activity monitoring, as everything runs on the edge. So what are the real-world edge AI implementations? The first one is a thermal vision used for a people counting. Why to count people? There are multiple use cases, like people want to know if everyone left the building in case of fire, for example, and they want to know how many customers are coming to their shop during some special hours, etc. So why thermal camera? Why not regular camera? Because in this case, we have very high contrast between the warm human body and the background. So we can easily recognize the moving people here. And the thing is, it's GDPR compliant. So no one can complain, actually, that he's being recorded because thermal vision does not provide you with the details necessary to recognize the person by his face. And the AI models here were like the world standards. It's like YOLO 8, SWORD for tracking, etc. But what you have to do, you have to port them. You have to go through several processes like quantization, for example, which makes your models really, really small and tiny. Running on a device, it's like a few kilobytes sometimes, or even smaller, depending if you run it on the watch, or a GPU, like in this case, GPU from NVIDIA. I don't know if you're familiar with that, but NVIDIA is producing like GPUs for data centers, very powerful, but also graphical units for the computer gamers, video gamers, but also edge devices. This is called like a NVIDIA Jetson family, several versions of very small boards which you can use for edge computing, especially for a computer vision. The second example, it's quite interesting. It's hybrid, which means it requires both cloud and edge. And my customer was from West Africa, and he called me with a very interesting business case. The case is like, all over the world, I think it works the same. If you are playing music in a public places, like, I don't know, in the shops, here on the conference, or in peluqueria, or, I don't know, cafeterias or whatever, if you play this music, you have to pay a fee to a government organization which is responsible for managing the artist's rights. And this organization, when they collect money from all of those shops and restaurants, is supposed to pay back the royalties to the artist whose music was played in those places. The thing in Africa is they collect the money, but they have no idea who to pay the royalties, because no one knows which music, which song has been played in these places. So my customer asked me, could you create a device, a small device, which I can place somewhere near the speaker in any of those places, and the device will recognize the music constantly and report what was played, when, and for how long to the central system. So I will have the report and I will know who to pay back. So we did kind of a prototype. It was 400 units installed in 3 African countries, recognizing the music. What we did, we actually sampled every 30 seconds. We listened to the background sounds, let's say, for a short amount of time, and we send this data to the cloud for recognition. So something like a Shazam application. Perhaps you know Shazam, right? To recognize your favorite music. Works the same, but when we send this data, after a few weeks, we realized there are huge costs on the data transfer, because data transfer in Africa is expensive. It's definitely not cheap, and you have to pay for it quite a lot, especially that we use LTE. Because there was no fiber, there was no Ethernet, nothing. In some of those places, there was just like a very low range of GSM network which we're supposed to use. And sending data every 30 seconds makes the bill like for 400 devices horrible. And the idea was to have 4,000 devices at the end. So what we did, we combined it with the Edge AI classifier. So before the data was sent somewhere, we just checked on the device, is it music or is it anything else? Like speech, like noise, like cars approaching or something. And we saved like huge amount of data. And the statistics, finally, of the recognized model, recognized music in the cloud, they remain the same, almost the same. Maybe even if few of the songs have not been recognized, it's nothing comparing to the savings we have just because of implementing very small Edge AI classifier, which, by the way, was running on the CPU. There is no NPU, no GPU there. So small AI model quantized to do this one thing. The third example is from this year, from Hannover Messe, where we created a project with cooperation with Schneider Electric. And this is like a smart air conditioning system, let's say. They had also very interesting business case about dairy cows. If you are producing milk, you have hundreds or thousands of cows. To make a good quality milk, the cows need to live in a proper temperature, like between 5 to 20 degrees Celsius. And imagine places like Saudi Arabia, where you have 40 degrees during the day, -0, below 0 during the night. So the cows would not survive that. So they keep them in an enclosure, in a buildings, specially designed for that, somewhere on the desert. And they are very heavy running air conditioners, like I hope we have now, but it's getting warmer and warmer. I know if you feel that, at least I feel that. Anyway, the cows would not survive, it's too hot for them, and they will not give a milk in such situation. No? So they wanted to have a control device, because the air conditioners can be controlled using the automation drives from Schneider Electric, but what they miss is the data, and the data means where the cows are in the moment. If you have hundreds of them or thousands of them in one huge building, cows like to stick together, same as people. So they move in groups. One big group is moving to one corner of the place where you all still have to cool all of that place. So we installed a thermal camera, which you can see. No, it does work? No. Which you can see on the middle square on the ceiling. There is a black box, very small on the top. You have 9 zones on the ceiling and 9 square zones on the floor. The one single camera was monitoring all of those zones on the floor. And if cow or a person, in case of Hannover Messe first, enter the zone, the air conditioning is turned on. If more people or more cows enter the same zone, the aircon is turning with more power. But all of the others are turned off because there is no one there. There is no reason to cool down the place. And in countries like Saudi Arabia, where they have like huge dairy plantations, let's say, dairy farms, the savings is calculated between 45 to 55% just on the energy because of utilizing such solution. So again, there was a thermal camera, Edge AI model, looking at all of those zones and just telling the automation drives how many cows, more or less, are in the particular zone, especially if there is none of them, then turn off the air condition in that place. All right, let's wrap it up. Summary. Why our world really needs Edge AI model? First of all, to save the energy. I think that's the main message for today. Those huge data centers where we keep all of our data, where we work with all of our AI models, etc., they consume huge amounts of energy, right? So they need like a nuclear plant to power up just this place. When you can use your NPU or a GPU, in this case, with 200 milliwatts running on maximum performance, which is 0.6 tops, 600 million operations per second, without consuming energy. It's very little amount of energy. Then you should use it. To reduce the latency, to not wait for the solution. The study says, with the GPU, because when the study was done, the NPU was not like widely available yet. Average time of classification of an image, which means I classify this is a cow or a dog. That's the image classification, is 120 milliseconds in the cloud, comparing to 35 milliseconds when running on the edge without the communication. It's not because cloud is slower, it's because of the latency needed to communicate. To increase the security, especially in case of computer vision, when you can run your models and stream the video only to the device instead of sending it somewhere else. People don't want to be recorded, right, usually. People don't want to have their face somewhere on the internet without their permission, so they don't want you to record them using your cameras. But if you, for a security purpose or for counting purpose, you just use your Edge AI model and you, let's say, take the information from that, take the information about number of people in the place, it's good enough already. You don't keep the video, you just erase it from the memory, process in the memory on the NPU and remove it. And to be network independent. Imagine your autonomous vehicle driving somewhere without internet connection, and there is an obstacle, or there is a turn, or something. It has to work without internet. It can synchronize data later when it gets online, but it could not be like the main source of truth, because then the vehicle stops, or the robot stops, or whatever. Going back to the first slide, as I promised. Consumption of 0.012 kilowatt of energy means one image in the cloud, fully charging your iPhone, powerful edge GPU, running for over 1 hour, but there is a new player, NPU, running on the maximum performance for 60 hours. And I mean maximum performance when something is happening constantly, 24 hours, 7 days a week. But usually that's not the case. So imagine you could have your Edge AI embedded vision project running on a battery for 1 year. For example, when you have a license plate recognition or something like that, cars are not approaching always, all the time. They are approaching, waiting, there is no one, etc. So there is a perfect case where you can save a lot of energy, a lot of computing power, and a lot of latency, and a lot of data transfer. So actually investing in Edge AI brings a lot of savings to the end customer and to the world. Thank you. Thank you.